Picture absolute zero, not empty space, not darkness, not silence. Those things are something. We're talking about less than that. A state so alien our brains can't quite hold it. In a fraction of a heartbeat, the entire universe erupted from a point smaller than an atom. Space didn't expand into anything. Space itself was being created, carrying everything with it. Time started ticking. The laws of physics snapped into place like locks on a vault. We know this happened. The evidence is still here, floating through the cosmos as a faint microwave hiss, the leftover heat from that first moment. We've measured it. We've mapped it. The math checks out, but knowing that it happened doesn't answer the question screaming in the back of your mind. How does something come from nothing? What pulled the trigger? And if time itself began at the Big Bang, what does before even mean? The universe has given us clues. Some point to answers. Others just deepen the mystery. Let's chase them down. The Big Bang Theory is the leading explanation for how our universe began, and it describes a moment when everything we know, space, time, matter, started from an incredibly hot and dense state. Imagine all of space compressed into a tiny point, often called a singularity, where densities and temperatures were unimaginably high. Then, in an instant, this point began to expand rapidly, initiating what we now call the Big Bang. This expansion didn't happen into empty space. Instead, space itself was stretching. As the universe expanded, it cooled down, allowing for particles to form and eventually combine into atoms. Over billions of years, these atoms clumped together under gravity's influence, giving rise to stars, galaxies, and all the cosmic structures we observe today. One of the strongest pieces of evidence supporting the Big Bang is the discovery of cosmic microwave background radiation, an echo of the universe's hot beginnings, now cooled into a faint glow detectable from every direction in space. Additionally, the observation that galaxies are moving away from us in all directions suggests the universe has been expanding since its inception. While the Big Bang outlines the universe's explosive start, it also raises questions about what triggered that initial singularity and what, if anything, existed before it. Still, this model provides a coherent picture. Our universe began, not from a point in space, but from space itself expanding and evolving over time. Scientists believe the universe started from a singular point because of the compelling evidence provided by the Big Bang theory. When astronomers observe distant galaxies, they notice that these galaxies are moving away from us, and the farther they are, the faster they're receding. This suggests that, at some point in the past, all of space itself was once compressed into a tiny, infinitely dense point, a singularity where everything was packed tightly together. The predictions of Einstein's general theory of relativity support this idea, showing that under the right conditions, gravity would cause matter to collapse into a single point of infinite density and temperature. Furthermore, measurements of the cosmic microwave background radiation, the faint afterglow of the universe's earliest moments, align beautifully with the notion that the universe expanded from a hot, dense state. By extrapolating this expansion backward, scientists find that the universe's density and temperature would have become infinite at a certain moment, indicating the presence of a singularity. Although the laws of physics break down at this point, the mathematical models strongly imply that all of the universe's initial conditions could have originated from this one infinitely small point. This singular starting place is a logical consequence of our current understanding of physics and the universe's observed expansion. The notion of an initial cosmic explosion, commonly known as the Big Bang, is supported by a variety of compelling evidence that has stood the test of scientific scrutiny. One of the earliest pieces of proof comes from the observation of the universe's expansion. Using powerful telescopes, astronomers have measured the redshift of distant galaxies, an effect where light stretches into the red part of the spectrum as objects move away from us. This redshift indicates that the universe is expanding uniformly in all directions, suggesting it was once compressed into a much smaller, denser state. Another cornerstone of evidence is the discovery of the cosmic microwave background radiation. This faint glow is a residual thermal radiation filling the universe, acting like an afterglow from a hot, dense state just moments after the universe's inception. Detected accidentally in the late 1960s, this background radiation has a remarkably uniform temperature with tiny fluctuations that provide clues about the universe's early conditions. Furthermore, observations of the relative abundance of light elements such as hydrogen, helium, and lithium align precisely with predictions made by Big Bang nucleosynthesis models. These models describe how these elements formed during the universe's first few minutes, lending strong support to the idea of a rapid, explosive beginning. Altogether, the universe's expansion, cosmic microwave background radiation, and elemental abundance serve as a trio of powerful evidences. They weave a consistent story pointing toward a fiery, explosive birth, an initial cosmic event that set everything into motion. Could the universe have emerged without a specific cause? That's one of the deepest questions at the heart of cosmology. Some theories suggest that the universe might have just existed as a kind of quantum fluctuation, a spontaneous event with no cause in the traditional sense. Quantum mechanics tells us that particles can pop into and out of existence, seemingly out of nowhere, governed only by probabilities. Could the universe itself be a giant quantum fluctuation on an unimaginable scale? Alternatively, certain interpretations of the multiverse propose that our universe is just one bubble among countless others, each with its own set of physical laws. In this view, it's possible that universes can come into existence without precise causes, emerging as natural outcomes of a process we don't yet fully understand. But does that mean it has no cause at all? Or merely that the cause is beyond human comprehension? Some argue that asking for a cause presupposes a temporal sequence, something that might not apply at the universe's genesis. So, while a universe without a specific cause remains speculative, it challenges our very definitions of origin and existence. When scientists talk about nothing, in a cosmological sense, it's a lot more complicated than simply the absence of anything. In everyday language, nothing suggests emptiness, a void with no matter, no energy, no space, no time. But in the universe's grand story, nothing often means something quite different. It refers to a state where there are no classical entities, no atoms, particles, or energy as we know them. Yet this nothing isn't necessarily the complete absence of everything. In quantum physics, even what we think of as empty space or a vacuum teems with fleeting particles popping in and out of existence. It's a bubbling sea of probabilities, a strange kind of nothing that's actually filled with potentialities. This idea challenges our intuition. Because if nothing can still give rise to something, as quantum fluctuations suggest, then the boundary between existence and non-existence blurs. It raises profound questions. Was the universe born from a state of pure quantum uncertainty? Could nothing contain the seeds of everything? These notions push the limits of our understanding, blending philosophy with science. Ultimately, nothing in a cosmological context may not be an absolute void, but a condition that inherently contains the potential for all that exists, an almost paradoxical foundation from which the universe itself could emerge. Rather than an absolute emptiness, it might be better thought of as a fertile ground of quantum possibilities waiting to be realized. The idea of nothing is more puzzling than it might seem. When physicists talk about the universe beginning from nothing, they often mean a state without matter, energy, space, or time as we understand them. But is such absolute nothing even possible? Many argue that nothing is a philosophical concept rather than a physical reality. In quantum physics, even what we call empty space is teeming with activity. Thanks to quantum fluctuations, tiny particles flicker in and out of existence, suggesting that empty space still has a kind of underlying activity or potential. Some thinkers propose that rather than absolute nothing, there's always been some form of something, a fundamental fabric or energy that simply shifts form or fluctuates. Others suggest that asking what came before the Big Bang is like asking what's north of the North Pole, a question that might not have a meaningful answer because the concepts break down at such extremes. It's also worth considering that our understanding of existence is rooted in our perception of reality. Space and time themselves came into being with the universe. So perhaps nothing is a human construct, and the true nature of the cosmos might be something entirely different, something beyond our current grasp, where questions about existence itself become incroyably complex and even unanswerable. The more we delve into the origins of everything, the more we realize that nothing might be an illusion, hiding a deeper, more mysterious reality. Physicists often describe a vacuum or empty space as the absence of matter, no planets, stars, or planets, yet it's much more than just emptiness. In the realm of physics, a vacuum is a region where the density of particles is so extremely low that classical matter is essentially non-existent. But even in this apparent void, strange and fascinating things happen. Quantum physics shows us that what we consider empty space isn't truly empty at all. Instead, it's teeming with fleeting energy fluctuations, where pairs of particles constantly pop into and out of existence for a tiny fraction of a second. These so-called vacuum fluctuations are fundamental to understanding phenomena like the Casimir effect, where two uncharged metal plates in a vacuum experience an attractive force due to the energy of these fluctuations. Moreover, the fabric of space-time itself can ripple and bend in a vacuum, enabling wave phenomena like gravitational waves. In cosmology, a vacuum might also be a place where the energy density is extremely close to zero, but it still influences the universe's behavior. This subtle but profound concept underscores that what we think of as empty space is far from nothing. Instead, it's a dynamic, vibrant entity, an active stage upon which the universe's grand story unfolds, filled with quantum activity and the potential for everything to emerge from seemingly nothing. The idea of the quantum vacuum often confuses people because it sounds like complete nothingness. But in reality, the quantum vacuum isn't empty in the way we might think. Instead, it's a seething backdrop filled with tiny, fleeting energy fluctuations. Particles and antiparticles briefly wink into existence and then vanish again, in a constant restless dance that happens on scales so small they're almost impossible to see. This restless activity is a direct consequence of the principles of quantum mechanics, which tell us that uncertainty and fluctuation are baked into the very fabric of space. So the quantum vacuum isn't absolute nothing. It's more like a bubbling brew of energy, a restless sea of potential that sits beneath the universe's smooth surface. Some physicists theorize that these quantum jitters could have played a role in sparking the very birth of our universe, pushing it from a state of something rather than nothing. While it's tempting to think of the vacuum as empty space, calm and void, the truth is that it's a dynamic, turbulent foundation, hinting that even what looks like emptiness has a mysterious, energetic life of its own. Quantum fluctuation shakes up the classic idea of nothing being a perfectly silent, empty void. In the world of classical physics, empty space was seen as a complete vacuum, completely devoid of matter and energy. It was the backdrop against which things happened, but it itself was static and unchanging. But quantum mechanics paints a very different picture. Even in a perfect vacuum, particles and antiparticles can spontaneously pop into existence for tiny fractions of a second before annihilating each other. These fleeting events are called quantum fluctuations. Imagine a calm pond, suddenly rippling with unseen tiny waves. These are like the quantum jitters happening in the fabric of empty space. The vacuum is never truly still. It is restless and teeming with activity. These fluctuations aren't just random. They have real consequences. They can seed the formation of particles, influence forces, and even spark the birth of entire universes in some theories. This dynamic view of nothingness suggests that the universe's origin might not have needed a cause in the way we imagine, because nothing was never truly empty. Instead, it was a bubbling, jittery fabric full of potential. Every fluctuation could, under the right conditions, trigger the birth of something new. So what we once thought of as a void becomes a fertile ground for creation, challenging our deepest notions of what nothing really means. The idea that particles can spontaneously appear from nothing sounds almost magical, but in the realm of quantum physics, it's a reality grounded in scientific evidence. At the smallest scales, particles aren't bound by the everyday notions of existence and non-existence. Instead, the quantum vacuum isn't a true void. It's a bubbling froth of energy, where particles can pop into and out of existence in fleeting moments. This phenomenon, called quantum fluctuation, means that energy is never truly at rest, and the vacuum itself seethes with activity. Think of it like a restless sea of potential, where particles emerge for a brief instant, then vanish again, respecting the constraints of the uncertainty principle. This brief appearance doesn't violate conservation laws, because these particles are essentially borrowing energy from the vacuum, a process known as a virtual particle interaction, and returning it almost immediately. It's a dance of energy and probability, where the universe's fabric is constantly fluctuating beneath the surface of our perception. During the earliest moments of cosmic history, those quantum fluctuations could have been amplified, leading to the formation of the very fabric of space-time. So, while it might seem impossible for particles to suddenly appear from nothing, in the quantum universe, nothing is more like a seething, energetic pool teeming with potential, where particles continually flicker into existence for just a split second before vanishing back into the quantum foam. Uncertainty is a fundamental piece of the puzzle when we look back to the earliest moments of the universe. At such tiny scales, the rules of classical physics begin to break down, giving way to the strange and probabilistic nature of quantum mechanics. Instead of precise predictions, we're faced with a realm where only likelihoods and possibilities can be assigned. This inherent uncertainty means that the origin of the universe may not have been a single, definitive event, but rather a range of potential outcomes. Quantum fluctuations, tiny random variations in energy, likely played a crucial role just fractions of a second after the Big Bang. These fluctuations could have acted as seeds, guiding how matter clumped together and how structures like galaxies eventually formed. This means the very fabric of the universe was shaped by uncertainty itself, acting as an engine of creation rather than chaos. Furthermore, the uncertainty principle challenges our understanding of what nothing really is. If even empty space is teeming with quantum activity, then the universe's beginning might have hinged on a quantum event. A fluctuation so profound that it kicked off all of existence. So, in a sense, it's the unpredictable nature of quantum physics that might have ignited the spark from which everything emerged. The idea that the universe itself might be a quantum event sparks awe and curiosity. At microscopic scales, matter behaves in ways that challenge intuition. Particles exist as probabilities, appearing and disappearing, governed by quantum rules. If we look closely, space and time seem not smooth, but pixelated, made of quantum fluctuations flickering in the vacuum. These fleeting jitters, once deemed insignificant, could be the seeds from which the universe emerged. Some physicists suggest our whole cosmos might be an enormous quantum wave function, a superposition of endless possibilities, collapsing into reality when observed. In this view, the universe isn't just a classical expansion from a singularity, but a quantum event, a spontaneous emergence dictated by quantum mechanics. Reality, in this context, is a delicate dance of probabilities, waiting for the right moment to tip into existence. This perspective raises profound questions. Was the universe's birth a natural consequence of quantum laws? Could every universe be a quantum fluctuation within a vast multiverse? If the universe is a quantum event, then its origin perhaps lies in the fundamental uncertainty woven into the fabric of reality itself. Imagine a reality much bigger and more bizarre than anything we can easily grasp. The multiverse hypothesis. It suggests that our universe may not be the only one out there, but just one bubble in an immense, possibly infinite, cosmic foam. Think of it like a cosmic ocean, where countless universes, each with its own laws of physics and unique properties, drift and collide in a vast multiverse. Each universe could have different constants, particles, and even dimensions. Some might be tiny, others unimaginably vast. How does this idea link to the question of universe creation? Well, if our universe is just one bubble among many, it hints that the birth of our universe might not have been a singular, unique event. Instead, it might be one of countless spontaneous events in a sprawling multiversal landscape. Some scientists propose that fluctuations in a higher dimensional space or quantum processes happening on a multiversal scale could continually produce new universes, each popping into existence like bubbles on a cosmic surface. This shifts the idea of a universe emerging from nothing to a more dynamic picture, one where creation is a perpetual, perhaps even routine phenomenon across an endlessly expanding multiverse. It invites us to rethink what nothing truly means, suggesting that what appears as empty vacuum in our universe might be just a tiny pocket of a much larger, bustling multiversal reality. Here, the origin of our universe becomes part of a grander tapestry woven into the fabric of an infinite cosmic multiverse. It's a mind-bending idea. Could there be more than one universe, each emerging from its own unique state of nothing? When we talk about nothing in this context, we're not referring to a simple empty void, but to a complex, seething quantum vacuum filled with fluctuating energy. If these quantum fluctuations can spark the birth of our universe from a restless, energetic state, why couldn't similar processes happen elsewhere, creating multiple universes in a vast multiverse? Each universe might have started from a different quantum roll of the dice, arising from different configurations of energy and fluctuations in their respective vacuum states. Imagine, then, a sprawling cosmic landscape where these nothing states aren't identical but possess their own characteristics, different energies, varied quantum fields, or distinct physical laws at the tiny scales. These differences could lead to entirely separate universes, each with its own set of parameters, potentially unfolding its unique story over time. It's almost as if nothing isn't just the absence of everything, but a bubbling cauldron of possibilities, birthing entire universes, like bubbles in a cosmic champagne. The notion pushes our understanding of existence, suggesting that the birth of our universe might be just one chapter in a far greater, more diverse multiversal tapestry, each universe a product of its own quantum origins, from an equally mysterious nothing. Yes, many scientists find the idea that our universe is just one bubble among an infinite or vast number of others within a larger multiverse to be an intriguing possibility. Imagine our universe as a tiny foam bubble floating in a vast cosmic bath, with countless other bubbles, each representing their own universe, existing alongside or perhaps even interacting with one another in some manner. These models stem from theories like eternal inflation, a variation of the inflationary universe concept, which suggests that inflation didn't stop everywhere at once. Instead, certain regions continue inflating, creating pocket universes that detach from each other, each with its own unique properties and physical laws. This multiverse idea helps explain why our universe appears finely tuned for life. Perhaps we just happen to reside in a bubble where conditions are just right. It also opens up the possibility that additional universes could have different constants or dimensions, challenging our understanding of reality itself. While direct evidence for other universes remains elusive, since they might never be observable, these models serve as fascinating frameworks, expanding our perspective from a single cosmos to an entire cosmic landscape, full of endless potentialities and mysteries waiting to be unraveled. The idea of a multiverse opens a Pandora's box of profound questions, both scientific and philosophical. On the scientific front, one of the biggest hurdles is that the multiverse, by its very nature, lies beyond our direct observation. How do we test or falsify the existence of other universes when we can't see or measure them? This creates a sense of speculation that's hard to anchor in empirical science. Some theorists suggest that if our universe is just one bubble in a foam of countless others, then the laws of physics might vary from one universe to another. But without concrete evidence, these ideas risk drifting into the realm of philosophical hypothesis rather than scientific fact. Philosophically, the multiverse challenges our notions of reality, causality, and even the very concept of nothingness. If there are infinitely many universes, each with its own laws, constants, and perhaps even histories, what does that mean for the uniqueness of our own existence? Does it diminish the significance of our universe, or elevate the idea that anything that can happen does happen somewhere? It also raises questions about the nature of probability. If all outcomes occur somewhere, how do we assign meaning or significance to events? These questions push us to rethink our place in the cosmos and challenge our understanding of reality itself, making the multiverse a fascinating but perplexing frontier in both science and philosophy. Philosophy has long wrestled with the profound question, why is there something rather than nothing? Unlike science, which seeks tangible evidence and testable theories, philosophy explores the underlying reasons and existential implications behind our universe's existence. Some thinkers argue that the very act of questioning reveals that awareness of the nothing from which everything emerged is a fundamental aspect of human consciousness. This boundary between being and non-being prompts reflections on whether the universe's existence is necessary or contingent. For centuries, philosophers like Leibniz pondered whether the universe must exist or could have simply been an absence of everything. He famously asked, "Why is there something rather than nothing?" suggesting that perhaps a necessary being, such as a divine creator, must have brought the universe into existence to explain its presence. Others propose that existence might be a brute fact, something that exists without reason or cause, simply because it does. Modern philosophical debates also tackle the nature of nothingness itself. Is nothingness truly a void, or does it possess some latent potential? Does our subjective experience of existence hint at a deeper metaphysical truth? Philosophy doesn't always provide definitive answers, but it opens pathways for understanding the mystery, probing the very fabric of reality and challenging us to consider whether the universe's existence is a fundamental necessity or a surprising anomaly. Many philosophical traditions around the world have approached the origin of existence with fascinating variety. In ancient Greek philosophy, thinkers like Plato envisioned a realm of perfect forms, the eternal, unchanging blueprints for everything beneath, implying that the material universe is a reflection or participation in these ideal realities. Aristotle, on the other hand, proposed that everything has a purpose and a first cause, an uncaused, necessary being whose existence set everything else into motion, hinting at an inherent necessity in the order of things. Moving eastward, Hindu philosophy explores the concept of Brahman, an eternal, unchanging consciousness that underpins all reality. The universe, in this worldview, is a manifestation rather than a creation, a cosmic dance emerging from the infinite. In contrast, Buddhist traditions focus less on origins and more on the cyclical nature of existence, emphasizing that suffering and rebirth continue until enlightenment dissolves the cycle. Many indigenous traditions see the universe as arising from a sacred web, the result of divine or spiritual forces that are woven into the fabric of reality. Some interpret creation as a spontaneous act of divine will, while others view it as an ongoing process filled with mystery and reverence for the unknown. Across these diverse perspectives, a common thread emerges. The mystery of existence invites both inquiry and humility, reminding us that human understanding is but a reflection of deeper, often ineffable truths. That question, why is there something rather than nothing, has fascinated thinkers and scientists for centuries, and it continues to spark curiosity today. At first glance, it might seem straightforward. Why does anything exist at all instead of absolute emptiness? But as we delve deeper, the question becomes surprisingly complex. It pushes us to explore whether nothing is truly nothing, or if it's a sort of unknowable state that inherently contains the potential for everything. Some physicists suggest that the very fabric of reality, according to quantum mechanics, blurs the line between something and nothing, implying that nothing might be unstable or even impossible to define in a strict sense. Others argue that asking why anything exists might be a category mistake, trying to apply human reasoning to realms beyond our comprehension. In the realm of quantum physics, phenomena often seem to emerge spontaneously from what we perceive as nothing. This hints at the idea that the universe's existence could be a natural consequence of fundamental laws, rather than requiring a divine or external cause. While the question remains deeply philosophical, it challenges us to rethink what nothing truly means, and whether the universe's existence might be less inexplicable and more inevitable than it appears. It's not just about what caused the universe, but about understanding the very nature of existence itself. When pondering the origin of the universe, Some might wonder if belief or faith can fill in the gaps that science has yet to fully explain. While faith offers a powerful and personal way to find meaning, it doesn't provide testable or empirical evidence about how the universe actually began. Beliefs can give comfort and purpose, but they rely on individual perspectives and cultural traditions rather than observable facts. Science, on the other hand, seeks explanations grounded in evidence, experiments, and mathematical models. It explores what is possible within the parameters of natural laws, even if those laws are still being uncovered. That said, many people find that their faith and curiosity coexist harmoniously. They see the mysteries of the universe as a canvas for wonder, inspired by both scientific discovery and spiritual belief. Some question whether our understanding will ever be complete, if there are true boundaries to human knowledge, or if delving deeper reveals even more profound questions. Whether faith provides answers or simply inspires continued curiosity, it reminds us of the humility and awe we should hold when contemplating the grand cosmic story. After all, whether through faith or science, our pursuit is driven by an innate desire to understand where we come from and what it all means.